Yeah, hi Patrick.
Hi,
How are you doing?
doing good. How are you?
Good. All right, let's see. We left off with question 9 yesterday, so let's
Yes.
start on 10. I've copied it over. So how do you solve a system of 3 equations and 3 variables when it's in this format? In other words, when each equation has all the variables on the left and numbers on the right, and that's considered standard format.
Okay.
You know what the first step is?
Wouldn't you try to line up all the variables under each other, like all the x's go in one row, all the y's go in one row?
Well, they're lined up. I've already done that. Here's the key. What you want to do is create 2 more equations, number 4 and 5, that have a variable eliminated. And both of them need to have the same variable eliminated. So step 1 is, can you pick 2 of those 3 equations and combine them in a way that eliminates a variable?
No.
Actually, you
Not,
can. If you add equation 2 to equation 3,
oh yeah, there's no.
x goes away, right?
Yeah.
All right, so let's do that. What do you get when you add those 2 equations?
6y minus 12z equals 4.
10z,
10z.
correct. Now, for equation 5, we have to use 2 different equations. We can't use 2 and 3, but we want to eliminate the same variable. So we have to either use 1 and 3 or 1 and 2. Can you
Couldn't you?
go ahead?
Couldn't you use 1 and 3?
You can use 1 and 3, but you'd have to manipulate 3 a little bit. In other words, at the moment, none of those combinations will eliminate x. So you have to take one of these equations and multiply it by something. So if I have to do that, which one should I take and multiply it by how many such that I can then eliminate it in the next step?
Number 3, and you can times it by 2.
I could, but then I'm going to have to do subtraction, right? In other words, if I take number 3 and multiply it by 2, I will have a 2x. And I can still eliminate x, but I got to subtract one equation from the other. Well, most every student I have ever met likes addition better than subtraction. So knowing that, how about we take equation number 2 and multiply it by 2? Get minus 2x plus 4y minus 8z equals 10. And I'm going to run a line through that so I don't get confused. Because the most important thing when you're dealing with 3 equations and 3 unknowns is to be able to keep track of your equation. Because not only do you end up with a lot of equations on one page, but some are just multiples of the other. Now, do you see how I got the new equation 2?
Yes.
All right. Now notice that I can add the original equation 1 and the new equation 2. I can add them together and it will eliminate x. What do you get when you add them together?
You get 5y minus 6z equals 3.
Now I have whittled the problem down to 2 equations and 2 unknowns. And now this is going to allow me to solve for either y or z, whichever one I decide. And then I'm going to back up. Once I solve for one variable, I'm going to back up and solve for the second variable, and then I'm going to back up and solve for the third variable. So let's look at these two equations, 4 and 5. If I'm going to use elimination, I got to get something eliminated. Well, how can I eliminate either y or z? Notice that I cannot just subtract or add them at the moment. I'm still going to have a y and a z. So I've got to manipulate them in such a way that one of these variables will disappear. Well, what can I do?
I'm not sure.
Well, it's a little bit of a tough one. You kind of have to find a least common denominator. Okay? In other words, for me to eliminate y, what if I multiply equation 5 by 6 and I multiply equation 4 by minus 5? Now that's going to give me new equation 4 of minus 30y plus 50z. And I have to multiply the right side by minus 5 also. Don't forget, you can't just arbitrarily multiply one side by a number. You have to do whatever you do to one side to another. Now, you see how I had to find the common denominator?
Yes.
Which was really, it's not really a common denominator. Well, the common denominator is 30. And I get that by multiplying equation 4 by minus 5 and equation 5 by plus 6. So I'm going to run a line through those so I know that these are the two that I'm dealing with. Now, what can I do?
You can just subtract or add.
Add. Definitely add. In other words, the reason I multiplied equation 4 by a minus 5 was so that I would get a minus 30. And now I know I can add these two equations. And like I said, it's always much easier to add than it is to subtract. So when you set it up, you kind of want to set it up so that you're going to be adding. See how I get that?
Yep.
Okay. Now I've solved for one variable. What do I do next?
Did you plug it in?
I'm sorry, what?
Did you plug it in?
Into which one? I'm looking at a whole page full of equations.
You could plug it into 4 and 5.
Well, I only need to plug it into one. And do I plug it into the new 4 and new 5, or do I plug it into the old 4 or old 5?
Maybe the old 4 or old 5?
Yeah, because those are smaller numbers. Which one has the smallest numbers?
Number 5?
Yeah, so let's erase the line that I drew through it. Erase that, multiplying each side by 6. And plug in z equals minus 1/7. Wow, that seems a little strange to me. That's an odd answer. Let me make sure here. I didn't make a arithmetic mistake. No, that looks right. Now I have 5y minus 6 times minus 1/7 equals 3, which now allows me to solve for y. 5y plus 6/7 equals 3, which means 5y equals, well, 3 is 21/7 minus 6/7 equals 15/7. That's 5y. Divide everything by 5 and you get y equals 3/7. Okay?
Okay.
So I've solved for z. I've solved for y. Now I still have to solve for x. Which equation am I going to use to solve for x?
You could use number 1.
Well, you can use any of the first three. And notice that you want to use one of the first three because they're the ones that have the smallest numbers on. Okay? So if I have to choose from one of those first three and I'm solving for x, which one should I use?
You could choose 3.
Right. There's an advantage to that, is that there's no coefficient. It's a positive sign. So 3 is better than 2 just because in number 2 it's a minus x, and in number 1 it's a 2x. So always use the simplest equation that has the positive coefficient if you have a chance. So to solve for x, I've got x plus 4 times y, which is 3/7, minus 6 times z, which is minus 1/7, and I definitely recommend you do it this way. In other words, don't try to do any of this in your head. Always spell it out first so you don't make mistakes. And now I just have one equation and one variable, right? So
Right.
if I bring that down, I've got x plus 12/7 plus 6/7 equals minus 1, which is x plus 18/7 equals minus 1, which is x. I'm going to subtract 18/7 from both sides. So I get x equal minus 1 minus 18/7. What's the answer to that?
It's terrible, right?
It always gives people a little trouble, and it's only because of one thing. And it's because this is an integer. How many sevenths is minus 1?
7.
Yeah. So I need to find a common denominator here. So I really have minus 7/7, that's minus 1, minus 18/7,
18 hours.
minus 25/7, that's x. So you have all three solutions now. And that's the way you have to do these. Every one of them. You want to do it exactly like this. In other words, the first step is to pick a variable and eliminate it. The second step is to use two different equations and eliminate the same variable. You cannot eliminate a different variable in step 2. In other words, step 1, to get equation 4, I eliminated x, right?
Right.
Well, I got to eliminate x when I look at 2 of the other 3 equations. It won't do any good if I eliminate z. I won't be able to get anywhere. I've got to end up with equations 4 and 5 both missing the same variable. In other words, I need equations 4 and 5 to be 2 equations and 2 unknowns. I know how to solve those. So you're always, and I really recommend this system right here of numbering these things. And you can kind of see why. I ended up with 1, 2, 3, 4, 5, 6, 7, 8. I ended up with 8 equations on my page. And if you don't number them, it's really hard to keep them straight. So I definitely recommend numbering these equations after you write them. And when you manipulate one equation by multiplying it by both sides, keep the number the same and cross out the original equation so that you also don't get confused. And I don't mean you, I mean everybody. That's the way everybody should solve 3 equations and 3 unknowns. Now, why they made this so tough by bringing fractions in, I don't know. There's no real reason for them to make it that tough. And it is possible that I made a mistake somewhere along the line. In other words, there's a lot of math to do here. It's easy to make an arithmetic error. And sometimes when I get answers like -1/7 or 3/7 or 25/7, it makes me think that I might have made an error, because I would expect them to give you a problem where the answers were integers. I'm betting that if you take a test and you get 3 equations and 3 unknowns, that the answers will be integers, not fractions. But in this particular one, they came out to be fractions, and I can't see where I made a mistake. So I'm going to assume that's the answer. Now, if I had a lot of time, then I would go back into this equation and substitute my 3 answers that I got for x, y, and z, and see if indeed it's equal to -7. You know what I'm saying? In other
Yes.
words, if your life depended on you having the correct answers, if somebody held a gun up to my head right now and said, is that the right 3 answers? I would not say yes. I would go back and I would check that equation and make sure that the values I got for x, y, and z make that an equation. And if they don't, I've made a mistake. And if my life really depended on it, then I would also plug those same values into equation 2 and equation 3 to make sure that I had satisfied all 3 equations. I can't be certain by plugging in my answers to just one equation that I have the right answers. But if I plug them into all 3 of the original equations and each one of them remains an equation, now I'm certain. Now I would bet my life that I have it right. But only then, especially when you have fractional answers like this. All right.
All right.
The one thing you can be sure of is that you will not take a test that has more than one of these, because it took us 20 minutes to do it, right?
Right.
And I didn't really waste any time. So in other words, all of those kind of problems are going to be 20-minute problems. Now, let's look at number 11.
Okay.
Most students that I've ever dealt with hate word problems. They detest them. You the same way?
Yeah, a little bit.
Yeah. Well, there's a simple solution to word problems. And that solution is you start at the back. And the very first step is you define your variables. So if I'm starting at the back of this problem, how many variables do I have? And you can tell how many you have by looking at that.
3.
Okay, so what's x going to be?
The x could be pizza.
The cost of pizza. And it's very important to tell, because you may have problems where the answer is how many slices of pizza do you have? Well, this one specifically says what is the cost of one small pizza. So x is the cost of small pizza. And it may seem like I'm being extra picky by having you spell it out, but trust me, you want to spell it out. Just
All right.
I have here. So what would y be?
That could be the cost of a 1 liter soda.
And z?
The cost of a salad.
And that actually, no, they want you to solve for it. So to solve for it, we have to come up with what? 3 equations and 3 unknowns, right?
Right.
In other words, when you're looking at 3 variables, you know you have to have 3 equations in order to solve it. Well, now let's go to the beginning of the problem and start writing our equations. So the first part of sentence 1 says what?
At a pizza shop, 2 small pizzas, a liter of soda, and a salad cost $14.
How can I write that as an equation in terms of these variables?
2x plus 1y plus 1z equal 14.
Second equation?
It'd be 1x, 1y, and then 3z equals 15.
And finally, the third equation.
And then it'd be 3x plus y equals 16.
All right, so there's our system that we have to solve. And it pretty much becomes the same as the last problem. In other words, we have 3 equations and 3 unknowns. There is a slight difference in this one, and that is that one of the equations is already missing a variable, z.
All right.
Okay, but we still, that actually almost makes it more confusing. So let's first start by numbering our equations. Which variable should I eliminate first?
You could eliminate y.
With which 2 equations?
Well, any two. You could do 1 and 3.
Okay, or I could do 1 and 2. What do I have to do?
Just subtract.
Right, okay.
Yeah.
So in equation 4, let's use 2 minus 1, or 1 minus 2. What does 1 minus 2 give you?
-1.
Well, what equation does it produce? I'm going to subtract 2 minus, or I'm going to take equation 2 away from equation 1. What is the result?
That'd be x plus 3 plus 1z, I mean, -1z equals
Well, now hold on. We're doing 1 and 2. So I got z minus 3z.
Which would be -2z.
Right. And 14 minus 15 is -1. Okay. So I've eliminated y. So I know that I have to eliminate y for equation 5. Now which 2 equations of the original 3 do I have to work with? Only 2 I cannot work with are 1 and 2. I can work with either 1 and 3, or I can work with 2 and 3.
You could do 2 and 3,
Okay.
or 1 and 2. I mean 1 and 3.
I already did 1 and 2.
Yeah, 1 and 3.
1 and 3 would work. So, and again, you have to subtract, right?
Right.
So are we going to subtract 3 from 1 or 1 from 3? We could do it either way.
1 from 3.
Okay, what do you get?
You get x equals 16. I mean, equals 2.
Get that z term.
Oh, then it'd be x plus z equals 2.
Well, now if we're subtracting 3 minus 1, then we have 0z minus this z. So that gives you minus 1z. And then 16 minus 14 gives you 2. Okay? Very, very important to distinguish, first of all, whether you're going to be adding the equations or whether you're going to be subtracting them. Okay? And notice that because I'm subtracting, I could actually do any of these in any order to get rid of y. Well, you'll notice you had a little bit of problem subtracting 3 minus 1. You wouldn't have had as much problem doing 1 minus 3 because 1 has z in it. So you would have had the z minus no z. You would have ended up with a positive z. Okay? So there's a little bit of an art to figuring out which equations to use and whether you want to subtract or add them. But nonetheless, we've got an equation 4 and 5. Now, how can I solve for one of those variables?
Could you just subtract?
Okay. Which from which?
You can subtract 5 from 4.
Okay, what do you get?
You get
This is where it's a little tricky. In other words, it's a little tricky because we have a negative sign there, we have subtraction going on, and we have a negative sign there. So it's really easy to make a mistake. So be very careful. The x's are going to disappear, and that's what we want. We want to eliminate another variable. But what goes right here?
Would be negative z? Or negative 3z?
No, you had it right the first time.
Z.
Yeah, that's why subtraction is so much harder. Here's what we're doing. We have minus 2z minus a minus z. Well, that's minus 2z plus z, which is equal to minus z. So if I'm going to subtract these two equations, that's what I get. And what do I get for the number? What's minus 1 minus 2?
Negative 3.
Yeah. Which means z is equal to what?
Z is equal to 3.
Okay. Which means x is equal to what?
I mean, x is equal to...
And you're always going to go back to either equation 4 or 5.
Yeah, so x is equal to 5.
Yeah, in other words, 5 minus 3 equals 2, so x has to be equal to 5. And now we got to solve for y, which is the easiest, and in order to solve for y, we have to find an equation that has y in it. Okay? Well, the simplest one is which one to solve for y?
Me too.
Yeah, 3. It doesn't even have the c in it. So we know that y is equal to 16 minus 3x. X is 5. So y must be 16 minus 15, 1.
All right.
Now, because it's simple enough to do, on this one, I'm going to check my answers. In other words, the last one had all those fractions. It wasn't so simple to check. But if I've got time, I'm checking it. Okay? Well, this one seems like a pretty good one, number 2, to use to check it, right? We got x, which is 5, plus y, which is 1, plus 3 times z, which is 3. Is that equal to 15?
Yes.
I'm now 99% sure that I got the right 3 answers. In order to be 100% sure, I would have to try all 3 and make sure all 3 work. But like I said, there's always in other words, there's a point where you don't want to spend your time checking your answers. If it's a timed test and you know that speed is going to be a problem, getting through all the questions, well, I would just go through it. Especially when I get answers like this and I can check it really simple with one equation, I'm done with the problem. Even though I'm not 100% sure, I'm 99%. All right?
You want me to go on? Hold on, David.
Okay.
All right, I'm back.
Yeah, so now the only problem becomes one small pizza is x, right?
Right.
And we came up with x, y, and z. So the answers that go here are x, y, and z. That's as hard as you're going to get, is a problem like that, I think. All right, let's look at number 12. What's the parent function they're talking about? Y equals what?
We have number 12?
Yeah.
We just wrote right the equation?
There's the parent function. Y equals absolute value of x. Okay. Now let's place these 4 adjustments. How do I do the horizontal shift right by 3 units?
Would it be x and then inside the brackets or the lines, x minus 3?
Correct. So that'd be the first one. Now a vertical stretch of 2.
Wouldn't that be on the other side of the lines between the equals and the lines
outside the function, correct?
Yeah, function.
So there's the first 2. That's a horizontal shift right 3 units and a vertical stretch of 2 units. Oh man, I can't believe they did this. They said just a reflection. Okay. No, I cannot believe they did that. They didn't tell you which axis. Well, and they are different. In other words, if we reflect over the x-axis, that negative sign goes out in front like that. And if we are reflecting over the y-axis, the negative sign would go inside the parentheses, or the absolute value sign. They didn't specify, so they don't really tell us. Major flaw on their problem here. That definitely needs to say reflection about one or the other axis. And finally, the 4th transformation, vertical shift up by 5.
That'd just be outside of the absolute value function plus 5.
Yeah. And that's kind of the way to think about transformations and reflections, is that if they're vertical, they're outside of the function. If they're horizontal, they're inside the function. If I really did want to reflect about the y-axis, then this second step here would not be that. It would be the following. Let's say their instructions said reflection over y-axis. Well, now I got to put the negative sign inside the function, and I got to put everything else in parentheses like that. Now that represents a reflection about the y-axis. And it comes out a little different, notice. When I simplify that, I get 3 minus x instead of x minus 3. So that would be a reflection about the y-axis.
All right.
Guarantee you he'll make a comment on that at some point, because that's just not right. And I don't, now that I think about it, no, they are different. They're absolutely different. There's no way that that equation is the same as this equation. In other words, a reflection about the x-axis is not the same as a reflection about the y-axis. They are different. So they really needed to specify which axis they were reflecting on. All right, let's look at 13. You have Inspire?
Yes.
You know how to do linear regression on it?
A little bit.
Okay.
Can you create a scatter plot and then put that into a graph?
Well, yeah, I have an Inspire, but I've never actually done linear regression on it. You have to make two lists. Okay? In other words, you can't really make a scatter plot unless you have two different lists. So you have to have list 1 that has the numbers 7, 9, 11, 12, 13, 14, 15 on it, and list 2 that has those heights. And then what you do in your Inspire is you say, give me a linear regression using lists 1 and list 2. And what it will do is give you the equation in y equals mx plus b format, and it will tell you what m is and what b is. In other words, it'll give you numbers for that. If you put these two lists in your Inspire and you ask it to do a linear regression, it will give you an m and a b. Let's say it gives you an m of 3 and a b of minus 10. Well, now you know your equation. Y equals 3x minus 10. That would be the equation they're looking for.
Okay.
Okay. Probably makes sense. Well, I don't think it makes sense for us to spend the time going through and putting these two lists in and actually doing the linear regression, especially since I'm not 100% sure I know how to do it in my Inspire.
He's almost got it in, David.
What's that, David?
He's almost got the data in, so he can take a stab at it.
He's already got it in?
Yeah, I have the A and B on a scatter, not a scatter plot, but
Okay.
a list.
Let's see if you can come up with the linear regression. They're gonna, when you request a regression, they're gonna give you a lot of choices. You can do a linear regression, you can do a quadratic regression, you can do an exponential regression. You want to do linear, which means put these things in a straight line, as straight a line as you can possibly fit to this data. So, do you know how to do that?
Yes.
Okay, what do you get for M and B?
Let me just put this in.
Yeah.
B is 83.24, and the M is 5.3. So, therefore, the equation is what?
So therefore the equation is what? 5.3
times 5.3. would be y equals 5/3 or 5.3
5.3x.
plus 83.24.
Yeah. And if we pick a point here and we just check to see if that is right, let's pick the smallest number. When x is 7, do you get 119.3?
Just give it a little more.
Let's see. Geometry.
You kind of have to do this manually. I'm going to multiply 5.3 times 7. I'm going to add 83.24. Well, that looks like it will give me 119, or awfully close.
Pretty close. Looks like it.
120.
And it's not going to be exact. Here's
It came out 120.34.
Yeah, here's what's going on. In case you're not quite sure of the concept of linear regression, let's say I gave you a bunch of points like this. And that's what they're giving you, is a bunch of, it's a scatter plot, okay? In other words,
Okay.
if I were to plot the points from the table, I would get something like this. I would not get all the points lining up in a straight line. Okay? The point is that now when I look at these, they look kind of linear, and if I were to try to draw a straight line that goes through those points, it would be something like that, right? Well, notice that the straight line doesn't actually go through any of the points, but it's the best fit. In other words, there's no other straight line I can draw that's a better fit than this one. I could maybe draw one like that, okay, but you could make an argument that that's a better fit to those points than the black one. But there's a very specific formula that your calculator uses, and it's based on the distance from the line of each of these points. And it's called a least squares fit. And what they do is they take the distance from the line, they square that distance, they add it all up, and whichever line gives you the least number, that's the line you use. And that's what you got when you did it by your calculator, was the line, well, whatever we got, 5.3x plus 80 something, that was the line that represented the best fit line to those points. And I don't really know how to describe it any better than that.
All right.
Now, it's not always a linear regression. Let's say I had a bunch of points that were like this. What kind of regression would you use if you were looking at a scatter plot of those kind of points?
Would be parabola.
Yeah, quadratic regression. In other words, I could fit a parabola through those points pretty easily. I'm going to have a hard time fitting a straight line through those points. In other words, I could do it, but the best I would come up with is maybe something like that, which isn't a very good fit. So there's all kinds of regressions. There's linear, there's quadratic, there's cubic, there's exponential. So it depends on what regression they're requesting. And you'll notice when you went to do your regression, you had all of those choices. You could have done more than just linear, okay? Now, the rest of the problem. What was the equation we came up with? Y equals 5.3x plus 83, something like that?
Yeah.
83.24.
All right. Now, for question A, use your equation to predict the average height of a 10-year-old. Well, notice that they don't have 10-year-olds on there. So how would you do that?
You'd use your scatter plot and the line of best fit.
No, you use this equation and x equal 10. In other words, remember what x is. X's are the ages, y are the heights. So if I want to find the height of a 10-year-old, I would make it y equal 5.3 times 10 plus 83.24. That's my height of a 10-year-old. Can your equation predict the height of a 40-year-old?
Yes.
Wouldn't you just plug in 40?
Yeah.
Well, you might think that it could, but think about how people grow. What happens when you hit age 15?
But at some point you stop growing.
Yeah. In other words, our scatter plot is going to look like something like this, but then at some age, you don't get any taller. So the linear regression really only applies to these points between the ages of 7 and 15. You cannot plug in 40 for x, you'll get a huge number. And as much as a 40-year-old might like to be 8 foot tall, that doesn't happen. In other words, you do not grow linearly. You grow linearly between the ages of 7 and 12 maybe, or 7 to 15.
All right.
But after that, you can't use it. And then it says, how about a 2-year-old? Well, I'm not sure you can even use it for a 2-year-old. I don't think it's linear between 2 and 7.
Oh, there you go. Yeah, see.
I'm not sure. I don't know for sure, but I suspect that you don't grow linearly from age 0 to 15. You might grow linearly from 7 to 15, and this would indicate such. In other words, if you look at the height of these children over here, that's pretty linear. If you draw a line on the top of their heads, you get a straight line. But if you can take it back to age 2 is the question. Maybe, but I kind of doubt it. A 2-year-old would be what? A 2-year-old, if I plug it in, would be 10.6 plus 83. So a 2-year-old would be basically that. And since it's in centimeters, I have no idea if that's how tall a 2-year-old is. But I doubt it. In other words, I doubt that if a 7-year-old is 120 meters, that a 2-year-old is 93. I think 2-year-olds are a lot shorter than 7-year-olds. They're not 80% of the height of a 7-year-old. You know what I'm saying?
Yep.
So you really cannot use this equation to predict either a 40-year-old or a 2-year-old. And the only way you can really know that is if you know something about the problem. In other words, if this was a blind problem where they weren't talking ages and heights and they just gave you an x and a y, then you might be able to use it to predict a 40-year-old. But knowing something about how people grow lets you know that it's not linear. And therefore, you cannot use this linear equation that we came up with to predict 40-year-olds or 2-year-olds. And at what point you can't use it, I don't know. I mean, I don't know if they'd have said, how about a 4-year-old? Well, maybe it works on 4-year-olds. I don't know. That looks like a 4-year-old right there, but she must be 7. So there's some considerations you have to take for all of these. Hold on. How did I lose my black? Oh, man. Here's the green. Oh, I had black there for a second. There it is. All right. I got it back. All right. 14. There's a graph that represents the cost of postage for a letter. Now, I don't know if you've ever bought stamps to send a letter. Probably not, since nobody uses snail mail anymore. But the cost to send a 1.5 ounce letter is the same as the cost to send a 1 7/8 ounce letter. In other words, they break it down by ounces. If it's anywhere from 0 to 1 ounce, you pay 39 cents. If it's anywhere from 1 to 2, you pay 41 cents, and so forth and so on. Okay? That's what
Okay.
if you go into a post office, that's what they'll, if your thing weighs 4.5 ounces, they're going to charge you 47 cents. Whether it weighs 4 ounces or 4.5 ounces, they're going to charge you 47 cents. So that piecewise function represents the cost of a postage letter pretty good. In other words, that's a good model to use. Well, now let's write a piecewise function that represents that. Okay, well, piecewise functions are, you always use f of x instead of y. The domain, it goes on the right. So that's x greater than 0, less than or equal to 1. What's y?
Wouldn't be y, you see 30?
39.
No. There we go.
And when x is greater than 1 and less than or equal to 2, what's y?
41?
Yeah. And so forth and so on until we get down to x is greater than 5 and less than or equal to 6, and that's 49. Okay, so you have all of those in between. I just don't want to take the time to write them all out. Question B, how much does it cost per ounce to mail a letter?
Looks like it costs 2.
Can't answer that. 1 ounce costs 39 cents, but 2 ounces cost 41 cents. So I can't tell you how much per ounce. That question makes no sense. See why? It's not double. In other words, if the cost to mail 2 ounces was twice the cost to mail 1 ounce, then you could answer that question. But it isn't. It doesn't go up. 2 ounces is not double 1 ounce. 2 ounces is only 41 cents. 1 ounce is 39 cents. So how much per ounce? It depends on how many ounces there are. If there's only 1 ounce, then it's 39 cents per ounce. If there's exactly 2 ounces, then it's half of 41, 20.5 cents per ounce. So it depends, the answer to this is it depends on the weight.
Okay.
And that is the correct answer. I don't know if it was a typo, if he meant to ask that question. It's an odd question. Maybe he meant to ask it and he wants people to know that you can't come up with a per ounce cost.
All right.
All right, let's look at 15. Let's see, we started at about quarter till, didn't we?
Yeah.
Yeah, okay. And I do have an appointment after this, so we go another 5 minutes. Okay. Now,
You know, David, excuse me, but we appreciate Excuse me, we appreciate your offer to go 5 minutes, but Patrick has another engagement he's going to go to, so this would be a good place for us to stop.
Okay, sounds fine.
And that'll be great with us, and we'll be back in touch obviously this year. So
Yeah. Well, you got some meat and potatoes with these questions. Notice that it took us an hour to do 5 questions tonight, and it took an hour to do 10 questions originally, and those were also pretty tough. So this material is very heavy with good stuff. If you can get through all of these questions, you're going to do well in this test.
Yeah, he looked like that he was plowing through pretty well with your help, so hopefully it'll translate to his quiz.
You know, I'm impressed, Patrick. Your math abilities are definitely way improved from the first time I ever talked to you.
Woohoo!
You definitely are. I noticed it yesterday.
I know it's being recorded. I don't care. All right, thank you, David. See you later.
All right. Bye-bye, guys.
Bye.
Bye. Mr. Whitey, 8 foot.